So as I mentioned, we are going to start the last chapter of the book. And similar to what we did so far, we kind of duplicate the concepts from particles to rigid body. If you remember the kinetics of particles, the last chapter we studied was impulse momentum. So today we're going to continue that for rigid bodies. And as you have seen in chapter 16, 17, and 18, the rotation element of rigid bodies that didn't exist for particles, that rotation element will create extra terms in acceleration, in force analysis, in energy, and we're going to have something similar for momentum. So with this brief introduction, I'm just going to jump into the start of the chapter. So chapter 19, as I just said, is about kinetics of rigid bodies. And the way we solve the kinetics is using impulse and momentum. So similar to the particles, when we used work energy, let's start from Newton's second law. When we use Newton's second law, we solve the equations at a certain point, like your quiz. You have the forces, external force, friction, internal force, everything, objects that may rotate or not rotate. So you solve Newton's second law at one moment. When you do work energy method, you integrate Newton's second law over a distance. So you go from position 1 to position 2. And you integrate and you get one single equation, which is a scalar equation, work energy relation, and you solve the problem. If you remember, for impulse momentum, we integrated Newton's second law over the time, not the displacement. So you go from point 1 to point 2, and you integrate the equations over time from time t1 to t2. You integrate it and you come up with the equations. And obviously the equations are not a scalar because momentum is vector. So you have to get x, y, z equations for that. Now, same thing happens here. So what we're going to learn here, first, angular momentum of a particle. You will see that the linear momentum of a particle can create angular momentum. And I'm going to define what that means. It's kind of like force creating moments. Linear momentum creates angular momentum. When we analyze this and learn how to calculate this, then we determine the momentum of a rigid body, which, as you may expect, is going to have one term for translation and one term for rotation. Then we go back to principle of impulse and momentum. And in case of no external impulse, conservation of momentum. And after that, we talk about impact. Here, the impact is slightly different, and we call it eccentric impact. And you see why we call it eccentric. So this is the ideas we're going to discuss here, the topics we're going to discuss in this chapter. Any questions so far? So let's see how we define the angular momentum for a particle. This is just a definition. If you have a particle with the velocity of v as a vector v and the mass of m, so your linear momentum is going to be mv. If the velocity is in this direction, as you see in this image, the linear momentum is going to be in this direction. And the distance of this particle from the center of rotation or the axis that you analyze is vector r. So the angular momentum of this particle is defined as r cross mv. And this is somehow similar, conceptually similar to when you define torque or moment. You get r cross f and creates a moment. Here, for linear momentum, r cross mv gives you the angular momentum. So angular momentum can exist if you have a particle moving with a velocity. And as you see here, the angular momentum is defined as cross product. So cross product of two vector is going to be another vector perpendicular to 2. So if r is in this direction and m is in this direction, r cross m, you're going to use your right hand rule going from r to the direction of m. This is kind of m. Go from r to m. Your thumb shows the direction of h. Now, considering all of cases we study in this chapter or this book or this course is planar motion, when you have velocities and positions all in a plane, h is always perpendicular to this and in z direction. In a general 3D case, for example, if you have a robot and you want to find angular momentum, you have to get a vector in any arbitrary direction. But for the cases we study, z is always, h about o is always in z direction. Any question? So this is a definition. Now, let's see how we can derive an equation out of this. We're going to go back to Newton's second law. Remember, for particles, the work energy method starts with Newton's second law. Impulse momentum starts with Newton's second law. So there's nothing conceptually new here. It's just we are analyzing Newton's second law from a different perspective, right? So if I consider Newton's second law as summation of forces applied on an object or a particle equals ma, and a is v dot, then we're going to play with this to see what we're going to get out of this. I'm going to do a cross product of r from left. So from the left, I'm going to get r cross f, and here I'm going to get r cross mv. Can I do this? If these two vectors are the same, you can do the cross product from right or left, because in the definition of h, or angular momentum, is r cross mv. I'm going to put r first here. So r cross f is equal to r cross mv dot, right? Any question? You guys are good? Now, I'm going to determine h dot. If I do h dot, which is dho dt, I'm going to get this term, ddt of r cross mv. So this is product rule. So you're going to get ddt of r cross mv plus r cross ddt of mv. So we can do this. Do you guys know what is dr dt? How much is dr dt? Do you remember from very first lecture of the book or the course? Anyone remembers anything?
I do not.
Mm-hmm.
Could it be velocity?
It's velocity. dr dt is velocity. So technically, if you simplify this, m is constant, so ddt of mv is going to be mv dot. So the first term becomes v cross mv. The second term becomes r cross mv dot. Now, how much is v cross mv?
Zero.
Zero. It's like a vector cross itself, or at least they're parallel. So this is going to be 0. Therefore, h dot or ho dot becomes r cross mv dot. Now recall from previous slide, if this is the case, and from your statics, hopefully you remember r cross f is the moment of the force. So technically, I'm going to substitute this by m, And I'm going to substitute this by h dot about O and get summation of moments is h dot about O. And this is for particle, right? So similar to linear impulse that you have summation of forces are I dot, I was, you remember? Sorry, L. We defined linear momentum as L. So summation of I was L dot. Here you get something like this. Summation of moments is H dot. Do you guys follow? Any question? Now, this is what happens when you have a single particle and you want to consider its angular momentum. Now, let's see what happens if you have a rigid body. For a rigid body, the linear momentum, if you suppose that rigid body can be divided into tiny particles of I with the mass of I, so each of them has its own velocity. Remember, this is a rigid body with general motion. If the rigid body has only translation, everything has the same velocity, so this becomes simply mv, right? But now that it has translation and rotation, each point has its own velocity. So L, or linear momentum, becomes mass times its own velocity for every tiny particle I. You add them together, you're going to get MIVI, and from the definition of center of mass, this becomes MVG. So technically, the linear momentum of a system with general motion is going to be mass times velocity of the center of mass. And these are all vectors. Any question? Now, how about angular momentum? If I consider my reference or axis of rotation on P, H about P is going to be H about P for every tiny object. So it's going to be Ri, if this is R for I, the position vector, cross Mi Vi, right? The summation of all these R cross MVs, when you integrate it over I, or if you use summation for tiny particles over the entire mass, this is what you're going to get. Now considering you can write the velocity of V in terms of velocity of P plus R cross omega using relative motion and expand this. If you expand this and write the whole thing, this is what you're going to get. H about P for the entire rigid body comes from this. And remember, because this is planar motion, H about P is already in Z direction. I may even remove this arrow here because it's already in Z direction. So we're going to get minus P VPX My bar plus VPY MX bar. And X bar and Y bar, similar to previous chapters, are the distance of G from your P, X and Y of your G in this coordinate system, plus IP omega. So this is the angular momentum of the entire rigid body about point P. And because this is planar, H about P is in Z direction. Again, there's like a half a page derivation here to go from this to this, but I try to kind of give you the concept and go through the final equation. If you calculate velocity of each particle with respect to G, you can still write H about P in terms of velocity of G. Okay? So you can use either of these two equations. Remember, H, or angular momentum, is still about P for both of them. But for one case, you use velocity of P and I about P. For one case, you use velocity of G and I about G. Okay? Any question? Now, we have determined the linear momentum. We have determined the angular momentum. Let's see if we can simplify this. Again, similar to chapter 17 and 18, we're going to look at special cases. The first special case is if you want to write angular momentum about G. So if I put my reference point on G, Y bar will be 0, X bar will be 0. So all of this is going to go away. So H is going to be I omega. And because the point is G, so H about G is going to be IG omega. The other case is when you have a fixed point, the angular momentum about a fixed point. Now let's go back to this slide. If P is a fixed point, VPX will be 0, VPY will be 0, so H is going to be again I omega. And we usually use letter O for fixed point. So technically, if you want to summarize, if you have translation only, your linear momentum is going to be MVG. Because there's no omega, this omega will be 0 for translation. H about G is 0. If you have rotation only, which means your object or your rigid that rotates about fixed point, this is going to be your angular momentum about fixed point. If you have general motion, which means you have linear velocity for G and angular velocity for the object, so your linear momentum is going to be MVG, and your angular momentum, you can write this guy, I about G is IG omega. Any question? Do you guys follow, or you feel bored or something?
Follow it?
So you don't have any question?
Not yet.
Not yet. So I suppose you speak for everyone, right?
Of course.
Okay, good. You are the president of the class. So now that we determined linear and angular momentum for a rigid body, we're going to go to the principle of impulse and momentum. If you integrate Newton's second law, F equals ma or mv dot, you can integrate it over time and get this term. So mvg1, which means initial linear momentum, plus external impulse applied to your rigid body is going to give you the final linear momentum. So this is linear impulse momentum relation, momentum and impulse. For the angular, if we go back to this equation that we got here, let me just go quickly here. You see summation of moments is H O dot. And we got HO here, or H about G, whichever you use. Then when you do that, you can write summation of moments about G creates an angular impulse. So you have initial angular momentum, you have external angular impulse. The summation of these two is going to give you the final angular momentum. Or if you want to write about the fixed point, initial momentum about the angular momentum about the fixed point, plus angular impulse, which is m dot dt integration over time, is going to give you the final angular momentum of your rigid body. So you have two sets of equations. Again, you don't see the vector sign here because we suppose this is motion in xy plane. So your I is going to be I about z, omega is about z, and everything is about z here. But for linear momentum, Vg and F could have x and y components. Now, if you consider the same footsteps that we went through in chapter 15, After establishing impulse momentum relation, we talked about the case that how about if there's no external impulse? If there's no impulse, initial and final momentum will be the same. We can say this for linear momentum. We can say this for angular momentum. So if that's the case, the conservation of linear momentum for a rigid body says if there's no external impulse from time 1 to time 2, T1 to T2, your mv at T1 and mv at T2 will be the same. And by v, of course, we're talking about velocity of center of gravity or center of mass. Okay? And if there's no external angular impulse, there's no moment or something, or the summation of moments are 0, the initial angular momentum and final angular momentum will be the same. Same goes if it's rotating about fixed point or if something rotates about center of mass. Now for this velocity, usually mass for a rigid body is constant if there's no external linear impulse. Your final velocity is going to be the same. For angular momentum, you may have a system that its I will change. If the I changes and there's no external momentum, omega has to change accordingly. So the omega times I will be constant. Do you guys have any example of an object with variable I that the omega has to adjust itself? Does this bring anything to your mind? Do you guys see my screen or the browser or no?
No, we just see the conservation of momentum.
Okay, so I'll probably have to stop the sharing and share the entire screen so you can see that. I don't know how good you can see this video, but many years ago when I started teaching dynamics, this was the world record for fastest skating spin. And this is the best example of and conservation of angular momentum. I'm going to play this and you guys see what happens. So I'm going to stop it here. This lady is rotating around its or her axis with legs out and hands out. So because I, the moment of inertia, is like mass distance square, this open leg creates a large number for her moment, momentum, mass moment of inertia about rotation axis. The hands are open, and those hands also increase I about Z. Now, when she starts kind of getting back to normal and kind of put her legs down and hands down, because this part of the body has less distance from axis of rotation, I decreases. Considering there's no external moment or anything applied to this lady and the friction at the foot is very small, you can consider conservation of angular momentum. So whatever angular momentum of this artist or I don't know, athlete is, when you decrease I, omega has to increase to compensate for that and keep I omega constant. And this is what you see here. You see it rotates and it starts kind of taking his hands, and you see as does that, it goes up to 308 RPM, which was a world record there. So this is kind of example. This is technically what, I don't know what the next video is, so let's just stop it because you never know what you're going to see. So let me just play this again one more time. You can see as the hands and legs are getting close to the body, the omega of the athlete increases, and obviously the highest omega is going to be when the hands and legs are completely compact to the body, and that's what you see. And I'm sure you can find similar videos in the web. Another example is this divers that when they jump and they're in the air, there's no external moment. So if they keep their hands and legs open, their rotation has some speed. If they collect their hands and legs close to the body, the I, this is what happens. The I about G decreases. For example, IG omega 1 is something. When you decrease IG, you have to increase omega so this remains constant. So the omega automatically increases to compensate for smaller I, and that's what happens. Any question? So do you guys get the concept how conservation of angular momentum works? It's kind of different from linear momentum because unless you lose mass, the velocity is not going to increase, right? But for angular momentum, you can have the same rigid body. Of course, it's not rigid because the body changes, but it's a system of rigid bodies. If you consider every part of the hand or leg, like bones are rigid, then when they come close to the axis of rotation, I decreases and omega has to increase to do that. Now, we're going to do an example here, a simple example to see how we can determine the angular momentum and angular impulse and relate them together. In this example, you have a gear which has a 30 kilogram mass. It has radius of gyration of, what is it? 125 millimeter. The radius of gear, or the effective radius up to the contact here, is 150 millimeter. So you have a gear rack. The rack B has a mass of 20 kilogram. The gear A has a mass of 30 kilogram. You apply a force of 200 Newton here, and you want to see how long it takes for this to get to the angular velocity of 20 radian per second. Apparently, you can solve this using Newton's second law, find the angular acceleration and then integrate it over time to get the velocities, but impulse momentum does that already, right? So if you consider to integrate from 0 to the time t, and your velocity goes from 0 to 20 radian per second, then you can establish an equation to solve this. So is the definition of problem clear? Yes? No? So let me share, okay, let me share the screen in my tablet so we can solve this problem. So you have a gear. I don't know how good I can draw this, but I try my best to see what we get. So you have a gear here. I'm not going to draw the teeth, but you get the idea. And this is your rack, right? At this point, M, rack and gear are kind of engaged. Gear A, rack B, and you have external force of P 200 Newton. These are is given as 0.15, and radius of gyration is 0.125. M of A, which is gear, let me just, M of A, which is gear, is 30 kilogram. M of B, which is the rack, is 20 kilogram. And of course, this is the ground, and it slides on the ground. Let me see if talk about friction or anything. Okay, the contact between the gear rack and horizontal plane is smooth. That means there's no friction here. So there's no friction here. This is smooth. How are we going to solve this? Any suggestion how to start? So to solve this, first of all, you have two separate objects. One object rotates about fixed point, O, and one object has translational motion. So the first step is to find out how much force you apply to each of them. So we technically need free body diagram for the gear and free body diagram for the rack. So I'm going to do the free body diagrams here. Let's say this is gear. You're going to have mg, right? You're going to have reaction force to these bearings here, and what else I have? I'm just going to redraw this part a little bigger so you can see what's going on. This is what happens. You have like gears, right? And here you have. So when I push this to the right, this teeth that is in contact is going to push the top gear to the right. So you're going to have an internal force. Let's just call it F. F is the force that rack applies to the gear. And the reaction force is applied from gear to rack, and that's F, right? So if, and these are supposed to be horizontal, but just put it that way. So if that's the case, you're going to have a horizontal force of F here. Remember, this 200, F is not necessarily 200 because this is internal force between the two. Do you have any other forces here to consider? Seth, do you have any other forces to consider for the gear? Okay. Now this is the rack. For the rack, you have its own mg again. You have the reaction force. Let's call it NB and NA so we don't confuse them because they're not the same. Then you have the reaction of this force F here at the contacting teeth. And you have the external force of P. Correct? Do I miss anything here? Melanie, is there anything missing here?
There wasn't friction, was there? Did it say it was?
There's no friction, no. Okay. Apparently, in the top one, you're going to have a horizontal reaction too. So here you have kind of like Rx. N is Ry, that's Rx, right? So considering the gear does not have translational motion, so if I write MA VGA 1 plus summation of forces dt equals MA VGA 2 from time t1 to t2. Because Vg is 0, technically what you get is summation of forces are 0, which means mg is equal to Na and Rx is equal to F. So this doesn't give us anything. Now, if I write the angular impulse momentum for the gear, here's what I have. I can write I about O, omega 1, oh, I don't need that thing, plus integration of summation of moments about O dt from T1 to T2. It's going to be I about O omega 2. So this is a meaningful equation, right? What creates moment about O? This is point O. The center of gear is the point O. What creates moment about O in this case? Does Rx, Mg, Na, or F create any moment?
The RX.
Yeah.
Rx create moment about O because Rx passes through O.
Oh.
Mg passes through O, Na passes through O. So the only force that creates moment is F, right? So if I rewrite this, I will get, and how much is initial omega? The problem says it starts from rest. So initial omega is 0. So if you simplify this, you're going to get integration of from T1 to T2. And T1 is also 0. So let's just go from 0 to T. And this creates a moment in this direction, right? So you're going to have F R dt, because this is all your moments, is this, is equal to I about O omega 2. How many unknowns I have here in this equation? How many unknowns? I do not know omega 2. This is what I'm looking for. I also do not know F. So I have two equations, one unknown. I cannot finish it. Now it's time to look at the rack. If you look at the rack, we can write linear impulse momentum relation for rack. Then I will have MB VG1 plus integration from 0 to T, summation of forces. And I know it's not going to go up and down. The motion is only in X direction. So I'm just going to put Fx because in Y it doesn't go up and down. dt is going to be MB VG2. Again, because the system starts from rest, initial velocity of G is 0. If you look at the forces in X direction, what forces we have in X direction? You have F, which is the action of this F, and you have P. So if I rewrite this, I will have integration of integration of from 0 to t p minus f dt equals mb vg2. Second equation. How many, I already had two unknowns. I created two equations. But if you see here, I also created the third unknown, Vg. So my unknowns are technically f omega 2 and Vg are unknowns, right? I have two equations. And we need one more. How we're going to get that? How we're going to get the third equation? And you need to look at the system here and come up with the third equation. Any suggestion? Lucas, can you suggest something for the third equation?
Would it just be V equals omega R? The
Exactly.
velocity of the rack.
Exactly. Because of the constraint here at point M, rack and gear cannot move independently. So technically, the velocity of point M here under gear is going to be, so Vm is going to be R omega. And because at this point, gear and rack kind of move together, so technically your third equation is Vg2 is equal to omega 2 times R. Now, if you look at, I'm going to rewrite all equations. Apparently, Fr is constant, so this integral becomes simple, and P and F are constant, so that one becomes simple. So if you rewrite those three equations, you're going to get from the first one, you're going to get Fr T is I about O omega 2. This is like equation 1, right? This is equation 2. You're going to get P minus F times T is M B Vg 2. And this is equation 3. Vg2 is going to be R omega 2. So you can simply substitute here and get it as M MB R omega 2. So I about O for the gear is going to be kg squared times mass, which is going to be how much? Kg was 0.125 times 30. R is 0.15, MB is 20, P is 200. I will not go through all the details of this solution because it's a simple two equation to unknown. So if you solve that, you will end up T, which is something you're looking for, 0.6215 second. And F, let me just calculate that. Is 100.56 Newton. So as you see here, you can use impulse momentum relation to solve this. The interesting thing about this example is that you have two objects. One object has linear momentum only. One object has angular momentum only. You write the equations, you relate them to one another, and solve for the unknown. Any question?
So does the weight of the gear impacts the rack? Like, should there be another force going down on the rack from the weight
Should
of
we
the
what?
gear?
Sorry, I couldn't hear you.
Should there be another force on the rack from the gear, from the weight of the gear?
Good point. First of all, if you look at the gear system, the weight of gear is tolerated by its bearing. So it's not that if you have I don't know if you can see my finger, it's not going to sit here and put its weight on the rack. Otherwise, they kind of get locked and don't move. Usually the rack and the two gears have little distance, so they're free to move. So the weight of gear is tolerated by its own bearing here. The other thing is, even if the weight is on the rack, that's normal force, and rack goes only horizontal. So technically, if that was the case, this NB would become larger. But this is not the case when you have the rack. If you had a ball or a cylinder sitting on the ground and moving, you're right. Then the weight will be transferred to the ground or to the plate under the disc or under the ball. But the gear has to be fixed here at its bearing. So the weight is going to be tolerated by that one. Did I answer your question?
Yeah.
Does it make sense?
Yeah, I think it does.
Okay. So are you, I don't know, some of you may not be mechanical engineering students, but for ME students, you deal with gears later and you see that you cannot just put the gears to sit on each other, because if the distance between center, if you have two gears, the distance between the center of the two circles has to be certain amount. If they go too close, it creates problem. If they go too far, there's going to be kind of clearance, and that also creates problem. So those distances are very sensitive. So technically, they are supported by their own shaft and bearings. Any other question? Okay, now let's try another problem. Let me see. I'm going to share screen here. So this is another problem. You have a square plate hanging here from one edge. The square has a mass of m and is suspended at point A by a cord. You apply a horizontal impulse. This is not a force, this is impulse. So it's like force integration of force over time already. You apply an impulse I here at this corner, and you want to find the location of the point P, which the plate rotates about it. Remember, this is kind of similar to the case that we had for the punching bag. Do you guys remember that problem? We said if you punch the bag from any point, any arbitrary point, it will have general motion. Now, if you kick this plate from the edge, the bottom edge, it will have a general motion, which means it's going to have a velocity, linear velocity or translational velocity, and angular velocity. So like I see, there will be a point that has zero velocity. And we want to find that point. So I'm going to give you a couple of minutes to write this down. And go to, oops, sorry. And while you're drawing this, I'm going to do it myself on my tablet so we can solve this. So each side of this rectangular plate has the size of, or the length of A, and you want to find the point P. So technically you want to find this distance, this distance. Okay, let's just share the screen now. So this is how it looked like. As I mentioned, okay, and you have this impulse of I applied here, right? So as I mentioned, this object has kind of general motion, so you need to write linear impulse momentum relation and angular impulse momentum relation. So for linear impulse momentum, what we have? Can you guys tell me what should I do for linear impulse momentum? So let's just do this. Linear impulse momentum. So if you look at your equations, you're going to have mvg1. And remember, if we have direction of x and y, this is going to create momentum in x. So we're just going to go with x plus summation of f dt equals mvg x2. Now this is impulse. The I here is already impulse. So it means I'm going to already have this, so I can just substitute that here. So I'm going to get M VGX1 plus I, and G is obviously in the middle, right? Is equal to M VGX2. This is going to be one equation, equation number 1. If I use angular impulse momentum, then I'm going to have H about G1 plus summation of M dt. It's going to be H about G2, right? So, and H about G is going to be I about G omega. How much is I about G for a rectangle? Do you guys remember? For a rectangle with the length, with the size of A and B, you had M AB plus B, A squared plus B squared divided by 12. Now you have A, so technically it's going to be M A squared plus A squared divided by 12, or right? So if I substitute this here, and remember the initial velocities are 0 because this is at rest, and then you start hitting it with this impulse. So if that's the case, this will be 0 and this will be 0. So if I simplify this, and something creates angular momentum, is going to be just I times this distance. So this is second equation. If I simplify it, I'm going to get I times this. How much is this distance? If this is A, and how much is this distance? D is going to be A over the square root of 2, right? So you're going to have I times A over the square root of 2 equals IG omega 2. So this is equation 2. And if I rewrite equation 1, I is M VG X2. Any questions so far? You guys hear me?
Oh, we hear you.
Any question? Is it clear what I'm doing? I just wrote the linear momentum equation and substituted, and then I did the angular momentum and substitute the values. So if IG is this much and the distance of this I is here, I just substitute those values. Now, if you look at this, the problem asks to determine the location of point P. Obviously, if I is input, you have two unknowns. You have MVG and you have omega 2. So if I simplify this, you're going to have I A square root of 2 is equal to M A squared divided by 6 times omega 2, one equation, and the other one, I is equal to M VGX2. I have two equations that I can use to find omega and I, but I'm looking for this distance here. I'm looking for this distance that I called it y. How I can get y from here? So technically, if you solve these equations, from the first equation, you're going to get omega 2 is I a over square root of 2 divided by m a squared divided by 6. So you can simplify this, get I over 6 square root of 2 ma. It's going to be your omega 2. From second equation, this is like first equation. From second equation, your VGX2 is going to be simply I over m. So I calculated two parameters here, but I think this 6 should be, this 6 should go to the numerator. Right? So I have calculated omega and VG, but how I'm going to find that y, the value of y here? Any suggestion? I'm going to give you a couple of minutes to think about this, okay? To see how you can get y. Just remember, what was the definition of y? What was the definition of point P? How we define point P in the problem? We said point P is a point that is like IC, the center of rotation for this plate. So it says determine the location of y of the point P about which the plate appears to rotate during the impact. So if P is kind of like IC, how we can relate omega and VG? Any suggestion?
Do you take VG divided by omega?
Yeah, so if P is IC, then VG is going to be R GIC omega. So you're going to go 2 and 2, right? So you just substitute, and this is going to be like y omega 2, correct? Actually, it's not y. This is your R, so it's going to be y minus a. Sorry, a minus y, or a by, let me just fix this. So it's going to be a over square root of 2 minus y times omega 2, right? Because if this is a over square root of 2 and this is your R GIC, then y is going to be, RGIC is going to be the difference of the two. So let me just substitute, see what we get. So for on the left hand side, you're going to get I over m. Right hand side, you're going to have a square root of 2 minus y times this guy, 6i over square root of 2 ma. So this I is canceled out by this I. this m is canceled out by this m. And if you simplify this, you are going to get the square root of 2a over 6 is equal to a over square root of 2 minus y. Or your y is going to be a over square root of 2 minus, and you can simplify this. If I multiply this by 2, you're going to get right? And your final number is going to be the square root of 2 over 3 times a. So this is your y. So you solve the problem starting from impulse momentum relation for translation and rotation. You find your omega, you find your VG. Now the problem asks find the location of P, which is IC. So this is the condition for IC. When you implement this condition and substitute values, you can find the length of Y. Any question about this? Yes, no?
Could you go over it one more time? Just like,
Okay, I'm going to start from the beginning, right? Let me just erase the schematic of the problem. So I'm going to redraw it so it's not too confusing. So you have a square plate hanging from one end, and you apply an impulse of I here. This is G. This I creates an omega and creates, because it's horizontal, it's going to create a VGX, right? So before the impulse, this was addressed. So we're going to start with impulse momentum relation for translation and impulse momentum relation for rotation. So MV plus linear impulse is going to be MV at the end, and H plus angular impulse is going to be H at the end, right? So I wrote all those values. Because it's addressed, the first term are going to go away. So you end up with these two equations. You end up with this equation and this equation. Remember, I impulse is your input. So I substitute the values. Meanwhile, I find I about G for the rectangle, for the square plate. And I substitute this. When I substitute, I get these equations. I'll calculate my omega and VG. Is it clear up to here?
yes.
Okay. Now, the problem could ask, for example, how much is the omega after the impulse? And you would be done here. Or how much is the velocity of G after impulse? You calculate this and you're done here. But the problem asks, what is the location of the point P, which is center of rotation? So technically your P is IC, right? And if this is IC, it looks like at this moment, your G is rotating about this point. You have the omega, you have the VG, you can relate it, considering this IC thing. right? You relate them and find your y. The rest is just simple calculations to get your y. So there are two key components to solve this problem. The first one is to get these equations right. Right? And write them down. When you find your velocities, the second key point is to understand point P is IC and implement the condition for IC, which is VG is R omega, just like that. Now, this R, you calculate it, omega, you have it from here, VG, you have it from here. When you put everything down, the only unknown will be your Y, and you calculate Y. Right? Make sense?
Yeah.
Okay. I think we passed 1 hour or something, so I'm going to stop it here. Let me stop recording.